A dynamic equilibrium is a state of balance between continuing processes. It's very important to understand the concept of a dynamic equilibrium as chemical equilibrium is a form of dynamic equilibrium. So the large difference here is that a dynamic equilibrium refers to any process. So it is not only with regards to chemical reaction, it can be any process. So it can be something as simple as a shop that allows a maximum of 30 people in. We know that there is a dynamic equilibrium there because there are people queuing outside. So every time one person leaves, there's one person allowed in on the other side. So we say it's at equilibrium because there's a balance of 30 people at all times, but it's dynamic because it's constantly changing. And then when 2 people were leaving, you would then be allowed to let 2 people in. So that is a simple example of a dynamic equilibrium. A slightly more complicated example is one in which you place a jar of water that is sealed in a room. We know that a certain amount of that water would evaporate to form water vapor, and that would continue until it reaches a point where the air becomes saturated, and at that point we say that dynamic equilibrium is established because every time a water molecule drops back into the liquid phase, another water molecule will be allowed to leave and become the gaseous phase. So we say it's dynamic equilibrium because the amount of liquid and the amount of gas remains constant, even though there's constant change between the two. Then we also learn in this section that reactions are reversible, basically saying that this reaction over here, we would react hydrogen and iodine to form hydrogen iodide, but we know that the reverse reaction is possible here too, which means that this hydrogen iodide would then react again to form hydrogen and iodine. So once again, we form an equilibrium where the concentrations of both sides remain constant. So it is that state of balance, although there is constant change between reactants and products. So all of these are examples of dynamic equilibrium systems, but only this one is a chemical equilibrium because chemical equilibrium only applies to chemical reactions that are reversible. There are 2 new concepts required to understand chemical equilibrium. The first one is the idea of what's known as either a closed or an isolated system. This is a system in which matter cannot enter or leave the system. It makes sense to us because if we had a system with just 2 gases in a beaker, the gases would obviously be allowed to escape. So a closed or isolated system is simply just when we put a lid on that system, that then enables us to make sure that all the matter that starts in the system remains in that system. The second concept is one that essentially just reverses what we have learnt thus far. And what we have learnt thus far is when we write a chemical reaction, hydrogen plus iodine, what that means is all of the hydrogen is then used up along with the iodine to form hydrogen iodide. What is also possible in many reactions is that they can be reversed. What that basically means is that 2 hydrogen iodide molecules can react with each other to break apart and form our original reactants once again. Reactions like this we say are reversible because we are saying that the forward reaction in which reactants are converted into products is able to be reversed where those products are converted into reactants once again. Obviously, if the forward reaction in this case is exothermic, meaning that it heats up the system, that must mean that the reverse reaction is endothermic, meaning the system would cool down. Now what this leads to is essentially an endless process in which reactants are converted into products, and those products are then converted into reactants once again, and you get this cyclical process known as chemical equilibrium. In order to illustrate this idea, I'm going to start out with a system in which we imagine that we have 10 hydrogen molecules and 10 iodine molecules, and obviously at the start, since we have only added these, there's no hydrogen iodide. We know that these react with each other in a ratio of 1 to 1, so let's say that 5 hydrogen molecules react, at the same time 5 iodine molecules react, we know that it produces twice as many hydrogen iodide molecules, which means that we produce 10 hydrogen iodide molecules. Now at this point, there are enough hydrogen iodide molecules for the reverse reaction to start, which means that now we have hydrogen iodide that is being used up to produce hydrogen and iodine. And at the point where the same amount of hydrogen and iodine are being converted into hydrogen iodide, we say the rate of the forward reaction, at the point where the rate of the forward reaction is equal to the rate at which the reverse reaction is converting products back into reactants, we say that we have established a chemical equilibrium. We say this because at that point, it looks like the amount of each substance present remains constant, because every time one hydrogen is used up on this side, another one is produced as a result of this, so the net change to the amount of hydrogen or the amount of hydrogen iodide remains 0. So, very simply, once again, we know that a reversible reaction is one in which products can be converted back into reactants, and we say that chemical equilibrium has been established at the point where the rate at which reactants are converted into products is equal to the rate at which the products are converted back into reactants, and that is seen by a constant concentration of all agents present in that reaction. We know that our traditional chemical reaction is one in which our reactants, in this case nitrogen and hydrogen, are reacting to form products, in this case ammonia, in what we know here is the Haber process, an important process in the fertilizer industry. What we've also learned now is that some reactions, of which this is one, are reversible, meaning that as the reactants produce products, the products are then able to react and produce those reactants again. This creates a cyclical reaction or a cyclical process known as chemical equilibrium. Chemical equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. Now, what becomes important, especially in the fertilizer industry where the goal is to produce ammonia, is for us to be able to know that at equilibrium, how much of each element is present. And the way that we do that is with a constant known as the equilibrium constant, also known as Kc. And what Kc tells us is essentially the ratio in which our products are present to the ratio in which our reactants are present. So this is obviously done using concentration. We know that writing something in square brackets refers to the concentration, so this means the concentration of ammonia to the power of its exponent. That is part of the formula because we are saying there are 2 ammonia molecules produced, which means ammonia times ammonia. Because this is a ratio, we can often write them as fractions. So the ratio of our products to that of our reactants, concentration of nitrogen to the power of its exponent, which in this case is 1, multiplied by the concentration of hydrogen to the power of its exponent. So what this can now tell us is by looking at our value for Kc, it can inform us as to how much of the reactants is present and how much of the product is present. So what we can see here is we can see that if Kc is a number that is much, much bigger than 1, what that means is that the concentration of ammonia is much, much bigger than the concentration of nitrogen and hydrogen combined. What that essentially tells us is our concentration of the products is greater than the concentration of our reactants. And what that tells us, or the way that we say this, is we say that equilibrium lies to the right. We are saying on balance there are more products present than reactants in this reaction. So for Kc, much bigger than 1, we say that equilibrium lies to the right. And then the converse is obviously also true, where if we now say that Kc is a number much, much smaller than 1, what that is actually telling us is the concentration of reactants is far greater than the concentration of our products, which means that very little nitrogen and hydrogen becomes ammonia, and as a result we say that equilibrium lies to the left. The equilibrium constant is a constant for a specific temperature. So you would often see an equilibrium constant quoted at a specific temperature. As an example, the equilibrium constant for the Haber process at 25 degrees Celsius is 6.8 times 10 to the power of 5. From this we can clearly see that this is a number that is far bigger than 1, which means that equilibrium lies far to the right, which tells us that at equilibrium there is far more ammonia present in a container than there is nitrogen and hydrogen. Please note here, this equilibrium constant is only valid as long as the reaction is at equilibrium, meaning for only as long as reactants are reacting to become products, and products are reacting again to become reactants. So when we say equilibrium lies to the right, we are saying there's more ammonia present, but the rate of the forward reaction is still equal to the rate of the reverse reaction. Once equilibrium has been established, we know that the rate of the forward reaction is equal to the rate of the reverse reaction, and the ratio of the concentration of the products to the concentration of the reactants remains constant as long as the temperature remains constant. Now, there are a number of changes that can be made to that reaction which would initially upset equilibrium, and we use Le Chatelier's principle to explain how the reaction responds to that. Le Chatelier's principle states that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Or, more simply put, the reaction will try to undo the change that we have made. So in this reaction over here, once it's at equilibrium, if we were to suddenly increase the amount of ammonia by adding ammonia to this reaction, we have now upset equilibrium because we've thrown this ratio out of balance, and the reaction is going to try to respond to that. So the initial response is that equilibrium is no longer in state, and the reaction tries to undo that by decreasing what I have increased. I have added an amount of ammonia, so the reaction's response is to decrease the amount of ammonia by favoring the reverse reaction. When we say that we favor the reverse reaction, what we are saying is that for this brief period of time, the rate of the reverse reaction is greater than the rate of the reverse of the forward reaction. By favoring the reverse reaction, we are decreasing the concentration of ammonia and increasing the concentration of hydrogen and nitrogen. This happens only for as long as it takes to re-establish that initial balance, or that ratio that we had there, that gets back to our constant Kc since we have not changed the temperature, and then equilibrium is restored and our forward and reverse reactions remain constant. Once again, we can make another change and see what the response is by saying what would happen if we were to suddenly increase the amount of hydrogen present in this reaction. So that is the change, the external change. Le Chatelier's principle says it will try to undo what we have done. It will try to decrease what I have increased. In doing that, it must favor the direction that uses up what I have added, which in this case is favoring the forward direction, which uses up nitrogen and hydrogen and creates or produces ammonia. So for this brief period of time, the forward reaction is proceeding at a faster rate than the reverse reaction, once again until equilibrium is re-established, at which point the forward reaction rate is equal to the reverse reaction rate. And because all of these reactions happen in a fixed ratio, the same Kc value will be re-established because the only change that can affect Kc is a temperature change. So Kc will remain constant as long as the temperature remains constant. We know that once equilibrium has been established, the rate of the forward reaction is equal to the rate of the reverse reaction, and the ratio of concentration of products to concentration of reactants remains constant as long as the temperature remains constant. We know that when we do make changes to the system, the Chatelier's principle governs how the system responds to those changes, and the change we're going to look at now is a volume or a pressure change. Now, it's important to notice here that volume and pressure changes are essentially or have the same effect, because when you increase the volume of a space, when you make more space available, that has a knock-on effect that automatically decreases the pressure because there's more space for the particles to move. In the same way, when you decrease the volume of a container, you are automatically increasing the pressure. So from now, I'm going to speak only about pressure changes, knowing that a volume change affects a pressure change and the result is the same. So the first example that we are going to look at is we are going to look at what happens when the volume of a container is decreased. So the change here is that we are decreasing the volume of a container, which automatically increases the pressure within that container. Now, we know that when there's a bigger pressure and a smaller space for those particles, the reaction by Le Chatelier's principle tries to undo that change. And since there is less space, the reaction tries to favor the direction that produces less stuff. So we count the number of gas molecules on each side of this reaction, and we can see that the forward reaction only produces 2 moles of substance, 2 ammonia molecules or moles, whereas the reverse reaction produces 1 nitrogen mole and 3 hydrogen moles, so 4 moles of substance. So the forward reaction clearly produces less stuff, which would take up less space. So in this change here, where we have decreased the volume and increased the pressure, we have said there is now less space available, so the reaction's response is to favor the direction that produces less stuff, that is to favor the forward direction over the reverse direction, meaning the rate of the forward reaction is greater than the rate of the reverse reaction, for a period of time, again all happening in this fixed ratio, until once again equilibrium is re-established and our Kc value remains the same because temperature has not changed, and then equilibrium is re-established where the rate of the forward is then equal to the rate of the reverse. All of these changes only have a periodic effect on the reaction where it favors a certain direction until it re-establishes equilibrium. The second option would be what would happen if we increase the volume of the system, which would thereby decrease the pressure. And we know that increasing the volume, decreasing the pressure means that there is now more space available. So the reaction favors the direction that produces more stuff. In this case, the reverse direction produces 4 moles. So we say that the rate of the reverse reaction is temporarily greater than the rate of the forward reaction until, once again, equilibrium is re-established and the ratio of products to reactants reaches that value of Kc, where we say, once again, the rate of the forward equals the rate of the reverse reaction. There is a complicated explanation for why exactly this does not have an effect on Kc. If you're interested, you can look into partial pressures, but for now, it is enough to understand that the only factor that can change your value of Kc is a temperature change. We know that once equilibrium has been established, the rate at which the forward reaction progresses is equal to the rate of the reverse reaction, and the ratio of product concentration to reactant concentration is constant in a value called Kc for a specific temperature. Now, we know that it is possible to make changes to a reaction while it is at equilibrium, and Le Chatelier's principle governs the response to that change, where Le Chatelier's principle essentially says the reaction tries to undo the change that you have made. So the change we are looking at now is a temperature change, where we are going to say what would happen if we were to increase the temperature of this reaction while it's at equilibrium. So the first thing to notice here is that this reaction, the forward reaction here, is exothermic, meaning the reaction mixture heats up for the forward reaction. Now we know that Le Chatelier's principle says the reaction is going to try to undo the change that we have made. So the external change is that the temperature is heated up. So the reaction is going to try to cool itself down by favoring the endothermic direction. And as we can see here, the endothermic is the reverse reaction, which means that temporarily the rate of the reverse reaction is going to be greater than the rate of the forward reaction, once again until equilibrium is re-established, where the rate of the forward is equal to the rate of the reverse reaction. Note though that a temperature change does mean that your value of Kc will change. We can determine how that value of Kc changes by noticing that by favoring the reverse reaction, we are decreasing the concentration of ammonia, increasing the concentration of hydrogen and nitrogen. What we can see that does is that the numerator of this reaction is decreasing while the denominator is increasing, which means that this number, the Kc number, is getting smaller. So the new Kc value is going to be less than the original Kc value when the temperature is increased. We can do another example where we see what would happen if the temperature of this was externally decreased. Once again, the Chatelier's principle says that we will favor the direction that undoes that change. So we tried to decrease the temperature. This reaction is going to try to counter that by increasing its temperature, meaning favoring the exothermic reaction, which in this case is the forward direction, which means that temporarily the forward reaction proceeds at a greater rate than the reverse reaction. The effect that this has is that the concentration of ammonia increases while the concentrations of nitrogen and hydrogen both decrease. We can see the effect that that has on our value of Kc here by seeing that the concentration of our numerator increases while the denominator decreases, which means that our value of Kc is going to increase, or we can say that the new value of Kc is going to be greater than the original Kc value. So this is the only change to a reaction that does produce a change to our Kc value, which is why it is important when specifying a reaction's Kc value to specify the temperature, because it is specific to that temperature. A quick note on the effect of a catalyst. We know that a catalyst provides an alternate path for the reaction to proceed. What a catalyst does is it increases the rate of the forward reaction exactly the same amount as it increases the rate of the reverse reaction. So a catalyst does not disturb equilibrium and therefore has no effect on our Kc value. In some instances, we refer to color change in equilibrium reactions as another way of evaluating how Le Chatelier's principle works. And essentially, what you are given is a fairly complicated equation, but to simplify it, you are told that the reagents, or in this case the reactants on this side, have a bluish color, the products on this side have a greenish color. And we know, and we are told that this reaction is at equilibrium. We can see that in this case the forward reaction is endothermic, which obviously then implies that our reverse reaction is exothermic. And then instead of being asked about how Kc is affected or which reaction is favored, you can now be asked what color the reaction becomes when certain changes are made. So in this example over here, the first question would say, what would happen if the temperature of this reaction were to be decreased? So now we know Le Chatelier's principle says that we are going to try to counter the change that has been made. So the temperature here has been decreased, which means this reaction is going to favor the direction that increases the temperature. That means we are favoring the exothermic reaction, which in this case is also our reverse reaction. And we can see clearly that the reverse reaction uses up green to produce blue. So we can say that the color change when decreasing the temperature is that this reaction becomes more blue because it uses up green to produce blue. The next change asks what would happen if hydrochloric acid, HCl, were added to this mixture. And what we need to remember is that ionic compounds ionize in water, which means that this would break apart into hydrogen ions and chlorine ions. So what this question is actually saying is that by adding HCl, we are increasing the concentration of chlorine. By increasing the concentration of chlorine, we are increasing our reactants. And Le Chatelier's principle says that we're going to try to undo that by favoring the opposite, favoring the direction that reduces the amount of reactants, which means we favor the forward direction, which produces more green components, which means that by favoring the forward reaction, we are producing a more green solution. The third change asks what were to happen, or what would happen if we added more water to this reaction. We can clearly see that we have water present in our products. Le Chatelier's principle says we are going to try to counter that by favoring the opposite direction, which in this case is our reverse reaction, because the reverse reaction uses up water, and in so doing it decreases the amount of green and increases the amount of blue in this solution. And finally, question asks what happens if we add sodium chloride to this reaction. Once again, we know that sodium chloride is an ionic compound which would dissolve into sodium and chlorine. So once again, we are increasing the chlorine ion concentration, and Le Chatelier's principle says we favor the direction that undoes that. In this case, that is the forward direction, which uses up uses up blue components and produces green components. So color change is just another way of testing Le Chatelier's principle. They are essentially asking you to say if we are favoring the forward reaction, we are producing more green, so the reactant or the reaction solution becomes more green. If we favor the reverse reaction, the reaction becomes more blue. We know that a dynamic equilibrium is one in which the forward process is equal to the rate of the reverse process. So as an example of that here, we have created a saturated salt solution, meaning that we have added sodium chloride to water until it is saturated, meaning no more sodium chloride can be added to form an aqueous solution anymore. So here's our saturated sodium chloride solution. And what we can demonstrate here is once again known as the common ion effect, where we will find that if I add hydrochloric acid, which we know ionizes to form hydrogen ions and chlorine ions, I'm going to increase the concentration of chlorine ions in solution and thereby upset the equilibrium, and we would expect to favor the reverse process here, which produces more sodium chloride, and we see that in the form of a white precipitate. We can see that the solution goes cloudy, and as we observe this, we'll see that that precipitate drops out and drops to the bottom of this reaction. Note here that this is a dynamic equilibrium. There's no chemical reaction happening here. This is a physical process where solid sodium chloride is being ionized into sodium ions and chlorine ions, and now the reverse process is where those sodium and chlorine ions are combining again to form a solid white precipitate, which we can see being deposited on the bottom or at the bottom of this test tube. We can demonstrate the way in which Le Chatelier's principle governs chemical equilibrium by making changes to a reaction and seeing how that solution changes accordingly. So the reaction that we're working with here is cobalt chloride that reacts with water. Here we have cobalt chloride. You can see that it is this dark blue or purple color, and we are going to add some water to this solution, which now sets the forward reaction in motion. The forward reaction here, cobalt chloride plus
water produces cobalt hexahydrate and chlorine ions, and as we can see, we have formed a slightly pink solution, and we can see that it's at equilibrium here where there is a certain amount of blue still present in the solution. So now what we can do is, since we can see that the enthalpy change is negative here, and that means that this forward reaction is exothermic, that means that if we were to add this solution into a hot water or into a hot water bath, we would see that by adding heat we are going to favor the endothermic direction, because Le Chatelier's principle tells us that the reaction works to undo the change that's been made. So by adding it into a hot water bath, the reaction is going to favor the endothermic direction. We would expect to see this go a darker shade of blue. So I'm going to do that and leave that for the time being. While that proceeds, I'm going to demonstrate the common ion effect with another reaction. So once again, we start with our cobalt chloride. We add water to that reaction, to that solution. Once again, we form a mixture that is at equilibrium. And now what I'm going to do is I'm going to demonstrate that by increasing the concentration of one of the products here, in this case, we can see that one of the products is chlorine ions, and we know that hydrochloric acid, when it ionizes, form hydrogen ions and chlorine ions. So by adding hydrochloric acid to the solution, I am adding a common ion, which is why this is called the common ion effect. And what that tells us is that I'm increasing the concentration of one of the products, which means that I should favor the reverse reaction, and we should see the solution turn more blue, which we can see happening here. So it's important to note here, and what this demonstrates, being the common ion effect, is that it is not necessary to add specifically only chlorine. You can add something that contributes to the overall number of ions, and that will still change the concentration and therefore the equilibrium position. What we can see in this reaction over here, we have very clearly favored the reverse reaction. The reverse reaction produces more cobalt chloride, which is blue in color, and we can see we have produced a more blue solution. What we can now also do is we can move this into a cold water bath. That cold water bath is going to once again force this reaction to respond by favoring the forward reaction, which is exothermic, to try and give off heat that is being lost to the surroundings. So we can move the solution into our cold water bath, and we can observe the changes here. So once again, this is all governed by Le Chatelier's principle, which says that once you have a reaction that is at equilibrium, any change that you make to that reaction mixture is going to be countered in a way that favors the reverse direction, or favors the direction that undoes the change that you've made. So in this case, when we added it to the hot water, it favored the endothermic direction to absorb that heat. When we add it to the cold water, we can see the color is going more pink. And as we favor the forward reaction here, because that is going to give off heat to counter the cold temperature that's been added here. And then finally, our common ion effect, which has shown us that by increasing the concentration of one of our products, we have favored the reverse reaction to try and decrease that concentration, again demonstrating Le Chatelier's principle, which always tries to counter the change that has been made. And here we can see that we have gone back to a pink solution in the cold water bath. We can demonstrate that Le Chatelier's principle applies to equilibrium changes when there are gases present as well, with the interaction between nitrogen dioxide and dinitrogen tetraoxide, where we have produced our nitrogen dioxide in the reaction between copper and nitric acid over here. That then goes on to produce copper nitrate, nitrogen dioxide, and water. We then isolate the nitrogen dioxide gas, that is this red-brown color of gas that we have over here, and we can then see that it establishes an equilibrium between these two gases, where the one is colorless and the other one is red or brown, or a red-brown combination. Now, since we can see that the forward reaction here is exothermic, we can then say that if we add this to a hot water bath, if we increase the heat of this reaction, we are going to force this reaction to favor the direction that takes in heat, the endothermic direction. So by adding it into a hot water bath, we expect a reverse reaction to be favored, which produces a more dark red or brown color, and we can see that when I do this here, we can see that by adding it into the solution, we can see that the color change favors the reverse reaction, which makes it a darker red or brown color. And we can see that by comparing the difference here between these two. And we can see that the one that has been in the hot water bath is slightly darker than the other. Now this can also be reversed by adding it now to a cold water bath, because we know that a cold water bath is going to remove heat from the system and therefore force the reaction to counter by favoring the forward direction, the exothermic direction that adds heat. And so we would expect a more colorless, or we'd expect this gas to go a lighter shade of red-brown. Again, keep in mind that whenever we add something into a cold water bath, we are also slowing the rate of reaction because there's now less energy available for reactions. So that change is going to occur over a slightly longer period of time. So while we leave that in the cold water bath, we can already see that there is or has been a change in that this one is now a slightly lighter shade of red-brown because we have produced more colorless gas by favoring the forward reaction. The other change that we know we can make to gases is that we can change the volume of the container in which those gases are found. In this reaction here, we can see that nitrogen dioxide takes up makes 2 molecules or 2 moles of space, where dinitrogen tetraoxide only takes up 1 mole of space. So we can imagine that when we increase the pressure on this system, when we decrease the volume, basically compress the syringe, we're going to increase the pressure, which means that there's now less space available, and Le Chatelier's principle says that this reaction is going to counter that by favoring the reaction that produces fewer molecules, which in this case we can see is the forward reaction. Also note here that there are going to be 2 changes. There's going to be an initial change. The initial change here is obviously going to be that there is now the same number of molecules in a smaller space, so the initial change is that the concentration will increase and it will become darker. And then after that change, if you pay attention, you can see very quickly that it does become lighter or more colorless. So here we go. You can see the initial change shows a darker gas form, and then after that it becomes lighter and clearer as time progresses because there's less space available, so the reaction favors the direction that produces fewer molecules. The opposite of this is also true. If I now increase the volume of this container, there is now more space available. More space being available means that we would now have more molecules being produced, so we're going to favor the reverse reaction. The reverse reaction here produces nitrogen dioxide, which is a red-brown color. Again, note that there will be an initial change here first. The initial change is that there's more space, therefore a smaller concentration or a lower concentration. So we will initially see the color get slightly weaker or dimmer, and then we will see it favor the reverse reaction that produces a more red-brown color. So we can see here the initial change there, and then as we favor the reverse reaction, we see that color get slightly darker. Temperature changes are very difficult to observe, so it's difficult to show here, but it's important to understand that a volume change is always going to have 2 effects. The first is that there's an initial concentration change, and the second is the favoring of the direction that produces more or less molecules depending on the change in space provided. We can demonstrate the effect that a concentration change to one of the reactants has on equilibrium, and Le Chatelier's response to that by using potassium chromate, which is yellow in color here, and we can see that when we react this potassium chromate with hydrogen ions, it is going to form dichromate, which goes orange in color. So we know that the common ion effect tells us that I can add an acid, which we know is going to increase the concentration of hydrogen ions in the solution, and thereby we start the forward reaction over here, and we can see that this reaction or this solution immediately starts to go orange in color, telling us that there is now dichromate present, and we have equilibrium lying slightly more to the right than to the left. Now we can also demonstrate the reverse of that by showing that if we decrease the concentration of our hydrogen ions, we are going to favor the direction that undoes that change, and that's going to favor the reverse direction, which will produce more hydrogen ions. Now, we know that hydrogen ions or acids react with bases, and hydrogen ions react with hydroxide ions. So if I add sodium hydroxide to the solution, what we will find is that the sodium hydroxide reacts with the hydrogen ions, and thereby we decrease the concentration of hydrogen ions in the solution, and in decreasing the concentration of hydrogen ions, we are going to favor the reverse reaction, which is going to try to counter that change. It is necessary to add quite a lot of sodium hydroxide because this is a low concentration of sodium hydroxide, but we can see that the solution is going more yellow in color because, once again, the hydroxide is reacting with the hydrogen ions that are present at equilibrium, and thereby decreasing our concentration of hydrogen ions. And when the concentration of hydrogen ions decreases, the reaction counters that with Le Chatelier's principle by favoring the reverse reaction that produces more hydrogen ions to undo that change that has been made. In the simple stoichiometric questions that we've done until this point, it was always a case of these are the quantities of reactants that we start with, what quantity of products are formed. We understand now that in chemical equilibrium we have this dynamic equilibrium in which reactants are forming products at the same time that products are forming reactants. So the reaction reaches an equilibrium where the amount of each substance present remains constant, and we need to be able to do calculations to determine what those amounts are. The simplest way to do this is to draw up what is called a SREC table. It is just an easy way of remembering that the SREC table should have the equation at the top, the amount of substance that you start with for each reagent in the reaction, the amount that reacts, the amount that you find at equilibrium, and then the concentration. So in this example here, we were told that we start by placing 6 moles of calcium carbonate in a closed or sealed or isolated container, which means that we start with 0 calcium oxide and 0 carbon dioxide. The question then goes on to say that at equilibrium, we find that we have 5 moles of calcium carbonate. So this is all part of the question, and then the question asks, if there's 5 moles of calcium carbonate at equilibrium, what quantities of calcium oxide and carbon dioxide remain, and what is the equilibrium constant for this reaction at this temperature? So we start out by saying that if we started with 6 moles of calcium carbonate and ended, the equilibrium is essentially the end point here, ended with 5 moles, that means that we must have used up 1 mole of calcium carbonate in this reaction. Now we know that if we used 1 mole of calcium carbonate, since the ratio of calcium carbonate to calcium oxide is 1:1, if we used 1 mole of calcium carbonate, that means that we must have formed 1 mole of calcium oxide. Same goes for carbon dioxide. The ratio of what we reacted to what we formed is 1:1, so we used up 1 mole there, we will form 1 mole here. What this tells us is that at equilibrium, if we started with 0 and added 1 mole, we must have 1 mole of calcium oxide, and the same goes for carbon dioxide, where we have 1 mole. And then the last point here was that the question asked, if the volume of the container is 2 cubic decimeters, what is the concentration of each of these? And the first thing to notice here is that calcium carbonate and calcium oxide are solids, and therefore they do not have concentrations, and their concentrations do not change. The only substance that is a gas that has a concentration is carbon dioxide. We know concentration is number of moles over the volume. We've just calculated number of moles is 1, volume is 2, concentration is 0.5 moles per cubic decimeter. And then finally, when calculating our equilibrium constant, it would normally be all of the products over the reactants, but once again, because solids do not have a concentration,
the equilibrium constant for this reaction is just equal to the concentration of carbon dioxide, and therefore 0.5. So once again, the SREC table is just a way that we answer these questions. It is not compulsory to answer it this way. You are welcome to do it using stoichiometric calculations. This is just an easy way for us to see that we start with a certain amount, some amount of that must be used up, which means that we end at equilibrium with this amount, and then because we know that all substances must react in a specific ratio to each other, that ratio is governed by the coefficients of each element in the reaction, we can then determine what amount of each we formed or used up, and then we can convert that into a concentration and use that to find our equilibrium constant. A slightly more complicated example of the equilibrium constant calculation using a SREC table would be something like what we have here. Now, this question does not give you the initial volume of the container, and what that normally means is that you are allowed to decide what the volume is going to be. So the easiest decision to make is to make that volume 1 cubic decimeter, because that allows you to easily convert between concentrations and volumes. Then this question reads, at a certain temperature, solutions of nitrogen, hydrogen, and ammonia, each with concentrations of 0.5 molar, are placed in a sealed container. What that tells us is that since the concentration is 0.5 molar, and we know that number of moles is equal to concentration times volume, and since we've selected an easy volume, we can directly convert those initial values to numbers of moles. So what this question has told us is it says that at the start 0.5 moles of each of these reagents is added to a closed or sealed container. They then go on to say that at equilibrium it is found that the concentration of nitrogen is 0.4 molar. Again, we can immediately convert that to a number of moles at equilibrium, which is obviously then also 0.4 moles. Now, once we've got this SREC table set up, we can now say, since we understand that if we started with 0.5 moles of nitrogen and ended with 0.4, we must have used up or reacted 0.1 moles of nitrogen. We can now also see that the ratio in which nitrogen reacts with hydrogen is 1 to 3. So for every 0.1 moles of nitrogen that reacts, we must have reacted 0.3 moles of hydrogen. And then what this also says is that when we are using up nitrogen, we will produce twice as much ammonia. As we can see, the ratio is 1 to 2. So when we use up 0.1 moles of nitrogen, we will produce or create 0.2 moles of ammonia. We can now, since we know what quantities we start with and we know how much reacted, we can say, since we started with 0.5 moles of hydrogen, reacted 0.3, we must have ended with 0.2 moles of hydrogen at equilibrium. We already know the amount of nitrogen at equilibrium, and we can calculate the amount of ammonia at equilibrium by saying, starting with 0.5, forming 0.2, we must end with 0.7 moles. Again, these can easily be converted into concentrations because our volume is 1, which means that this is a 0.2 mole per cubic decimeter concentration, and this is a 0.7 mole per cubic decimeter concentration. So to calculate the equilibrium constant for this reaction, we know that it is the concentration of our products, in this case ammonia to the power of its exponent, over the concentration of our reactants, hydrogen to the power of its coefficient, and nitrogen also to the power of its coefficient, which means that our equilibrium concentration, our equilibrium constant, can be calculated as follows. And
And what this tells us, the fact that this equilibrium constant is so much bigger than 1, is it tells us that equilibrium lies far to the right. We know that equilibrium lying to the right means that at equilibrium we will find more products than reactants, which makes sense here because we can clearly see I have 0.7 moles of products and only a combined 0.6 moles of reactants. Another type of equilibrium constant calculation is one in which you are required to use your equilibrium constant to find values that you would be able to use in your table to find your final answer. So a typical example is this one that we have here, where we've been told that the equilibrium constant for this reaction at this temperature is 4, and we are told that unknown amounts of X2 and Y2 are placed in a sealed or an empty container, which means that the initial quantity of XY3 is 0. And at equilibrium, it is found that the concentration of Y2 and XY3 are both 0.4. We are asked to find what these two unknown amounts that we started with are. We start doing that by using our equilibrium constant formula to find that the concentration at equilibrium of X2 is 0.625. We can then substitute that value directly into the concentration in our table, 0.625. The question has stated that we have a volume of 2 cubic decimeters, and that means that we can use this formula, number of moles is equal to concentration times volume. So we multiply each concentration by 2 to find the equilibrium number of moles, which means that we have 1.25 moles of X2 at equilibrium, 0.8 moles of Y2 at equilibrium, and 0.8 moles of XY3 at equilibrium. Now, since we know that we started with 0 moles of XY3 and ended with 0.8 moles, that means that we know that we must have formed in the reaction 0.8 moles of XY3. We can then see that the ratio of XY3 to X2 is 2 to 1, which means that we must have used up half that amount, half of 0.8, 0.4 in this reaction. We can also see that X2 reacts to Y2 in a ratio of 1 to 3, so 3 times 0.4, 1.2 moles of Y2 must have reacted. What we can tell then is that if we end with 1.25 moles at equilibrium after having lost 0.4, that means that we must have started with 1.65 moles of X2, and if we end up with 0.8 after having lost 1.2 moles, we must have started with 2 moles of Y2. I have put the entire question in the description for this video below, but essentially what we are now seeing is that we can use our equilibrium formula to find unknown concentrations that we can then substitute into our table. We can use number of moles as concentration times volume to find our equilibrium number of moles, and then because we know that only these two reactants were added at the start of this reaction, we can determine that there was 0 XY3, which means that we are then able to determine the amount of XY3 that was formed, and we can use our ratio in which these things react to find how much of each reacted, and then just work backwards to find our starting quantities.
A common way of testing chemical equilibrium is through a combination of a graph and a SREC calculation. So here is a typical example. The question states hydrogen and iodine are injected into a closed container at a constant temperature. The reaction reaches equilibrium according to the following equation. The graph illustrates changes that were made to the equilibrium mixture. Now, as we can see here, we have at T0 equilibrium is established because the concentrations of all agents present is constant from T0 to T1. So we say from T0 to T1, this reaction is at equilibrium because the concentration is constant. We can then see at time T1 the concentration of hydrogen spikes instantaneously. This can only be explained by adding a certain amount of hydrogen into this equilibrium mixture. So what happened at time T1 is a certain amount of hydrogen gas was injected into the system. We know that Le Chatelier's principle says that we would favor the direction that undoes that change, which is why we can see the reverse reaction is favored, that decreases the amount of hydrogen in iodine and increases the amount of hydrogen iodide in accordance with this reaction over here, that being the forward reaction. And then we can see from T2 onwards, once again, the concentrations remain constant, so we can say that this reaction is at equilibrium. This question then goes on to state the following. Initially, 0.3 moles of hydrogen and iodine are injected into the closed container that I've recorded here, 0.3 moles of each. And the container has a volume of 2 cubic decimeters. Equilibrium is established at 448 degrees, and the constant at this temperature is 50.5. We know that equilibrium constants are only constant for a specific temperature. We are then asked to calculate the amount of hydrogen and iodine and hydrogen iodide at equilibrium. We can do this with the aid of a SREC table. Note here that in your SREC table you must specify that S means the start number of moles, R means the reacting number of moles, equilibrium means the number of moles at equilibrium, and concentration, or C, is the number of the concentration at equilibrium. So once we have filled in our values here, there's not much more that we can do. We are forced to introduce a variable. So the way we do that is we say that in order for equilibrium to be established, a certain amount of hydrogen must react. We are going to call that amount X, and it is obviously removing from the amount of hydrogen, so we say a negative amount of X reacts. The same goes for iodine. Since they react in a ratio of 1 to 1, we can say that negative 1x moles of each of these is removed, and since the ratio here is 2 to 1, that must mean that we form 2x moles of hydrogen iodide. What we can then do is we can say that at equilibrium, that means we must have 0.3 minus x moles of hydrogen, what we started with, minus what reacted, and the same for iodine, and for hydrogen iodide we started with nothing, we formed 2x moles. But we know that in order to use our equilibrium constant, we need to convert this into a concentration. We've been told that the volume is 2 cubic decimeters, which means that our concentration here is 0.3 minus x divided by 2, because we know that concentration is number of moles at equilibrium divided by the volume which was given. Same goes for iodine, and the same goes for hydrogen iodide. And now we have a term for each concentration, and we can use our Kc expression to find our value there by substituting in all the values that we have just calculated and were given. We can say that we were given an equilibrium constant of 50.5. We substitute those terms for concentration in, and we can, by doing the algebra, solve to find that x has a value of 0.23. What this now tells us is we can say, since we know that 0.23 moles of hydrogen reacted, that means that at equilibrium we must have been left with 0.07 moles of hydrogen, the same for iodine, and 2 times that, 0.46 moles of hydrogen iodide, and then obviously converting that into the concentration, ending with a concentration of 0.23 moles per cubic decimeter of hydrogen iodide. So once again, it is important for us to understand what the equilibrium constant means, and once equilibrium is established, we can safely say that those values must have been established through the reaction. Since we were not given any other information, we are forced to introduce a variable, that being x, and we would say that in the reactants we lose an amount of x, negative x on each side, and since the ratio of hydrogen to hydrogen iodide is 1 to 2, if we lose 1 mole of x here, we must produce 2 moles of x there, and then once again we substitute these values for concentration into our Kc, and that allows us to solve for x and then answer whatever questions follow.